Buongiorno Edoardo, mi sente? Salve Edoardo, mi sente?
Buongiorno, sì, la sento.
Sì, perfetto. We also have Umair Rafik. Can you hear me, Umair?
Yes, Professor.
Okay, so we are ready to start. Welcome to this third lesson of the ATWP course. Let me enlarge the screen. Okay, in the previous lessons we laid the foundations by giving you some basic information about complex functions of one complex variable. What we will do this week instead is to address the topic of asymptotics. And let us see what is this about. In the first lesson, we compared numerical versus analytical approaches with their own pros and cons. Excuse me. Okay, here we are. Ciao Fabrizio, mi senti? Fabrizio, mi senti? Spero di sì. Okay.
Ciao Paolo, mi senti?
Sì, ora sì, ti sento, grazie.
Hai già
Perfetto.
cominciato?
È da un minuto, proprio un minuto preciso. È la prima slide questa.
Grazie.
Okay, we compared numerical and analytical approaches. Today we will be more specific. We will address asymptotic approaches, which among the analytical methods are an important subclass. The comparison can be stated in these terms. Typically, numerical methods, although in principle capable of giving you an exact answer within the accuracy of your machine, of course, they can be cumbersome or even not feasible when you deal with objects that are very large. That is, specifically when the dimensions of the object are large with respect to the wavelength. Because in that case, the number of unknowns, for example, imagine the number of basis functions in a method of moment discretization, or the number of cells in a finite element method, or the number of nodes in a finite difference approach, that can become extremely large, which means a huge amount of memory, and also the necessity of inverting huge matrices. Okay, even if you are able to arrive to a numerical solution, usually that solution does not give you much physical insight into what's happening in physical terms. That is, the wave processes that are that underlie the phenomena that you are observing. On the other hand, the asymptotic representations or asymptotic expansions of the same wave fields have several to arrive at are typically very simple. They provide you with a high degree of accuracy, typically with a small number of terms. Even just one single term in an asymptotic series can provide you an acceptable, even accurate result. And what's more important, they give you typically physical insight into the kind of wave species that are involved in the phenomenon you're observing. So for this reason, in this lesson and in the next one, we will provide some basic information. Good morning. No problem. We provide some basic information on asymptotic expansions. Note that such expansions can be derived in different ways. The topic is, of course, extremely vast, so we will give just an introduction to it. One possibility is to derive an asymptotic expansion directly from the equations, typically the differential equations that govern the wave field. For example, in the case of electromagnetic waves, you take Maxwell equations and you manipulate them to obtain an asymptotic representation of the solution. Or alternatively, you can cast your problem in terms of Integrand representations. For example, you can switch from Maxwell equations to some boundary integral representation of the field, and then apply asymptotics to those integral representations. In this week, we will address the first route. So in the next lesson, we will give the foundations of ray optics, whereas in the next week, we will address the topic of asymptotic evaluation of integrals. Okay, this is the outline of what we will do. So basically, what I said so far is that in this lesson and in the next ones, I will address asymptotic methods, which are to be compared with numerical methods. They provide you simple results and usually very accurate, of course, in some asymptotic limit, which is typically the limit of very short wavelength or high frequency limit. Okay. Okay, to introduce the subject, let us make a short tour with a specific example. So what I've called a behavioral survey to give you a flavor of the typical behaviors of asymptotic representations or expansions. We will start with a very well-known special function, that is the error function. The error function is defined as an integral. As you can see, there is an integral in the complex plane from 0 to the argument z of the function, which is on the left-hand side. The integrand is the Gaussian exponential e to minus u squared, and the integration is performed with respect to u. Then there is this numerical factor in front of the integral, which is inserted only in order to normalize the function. That is, when z tends to infinity, and imagine for the moment that z is a real variable, but then we will extend these considerations in the complex plane, then the integral is convergent at the positive infinity of the real axis. And that's a standard integral. It's a Gaussian integral whose value is the square root of pi divided by 2. So by inserting the reciprocal of that value in front of the integral, we normalize so that this function phi on the left-hand side tends to 1 when z tends to infinity along the positive real axis. Okay, this function, of course, is important in its own right. That is, it's used in a number of application areas, for example, in probability, statistics, and many other areas. And it is especially interesting in the subject of asymptotics because historically it has provided one of the earliest examples of what is known as the Stokes discontinuity in the asymptotic representation. That is something that we will address today. Okay, let's see how one could try to evaluate this error function. One possibility is to adopt a convergent expansion of the integrand, since the integrand is the Gaussian exponential, and the exponential function is an entire function. So we now know that it's analytic in the entire complex plane. It can be represented as the sum of its Taylor series with the initial point at the origin, and its Taylor series, whose radius of convergence is infinite, that's because it's an entire function, is the one that you can see here on top. So you see there is the nth power of minus u squared divided by the factorial of s, where s is an integer number that goes from 0 to infinity. This series is absolutely convergent for any complex value of z. It's uniformly convergent on any closed and bounded subset of the complex plane, or shortly, in any compact subset of the complex plane. Now, since this convergence is so nice, in particular, it's uniform, then we can switch the integral and the infinite summation and integrate term by term. The integration then becomes immediate because we just need to integrate those monomials. And so the result is this convergent series here, where in addition to the numerical factor 2 divided by the square root of pi, you can see there is the variable z taken outside of the infinite summation, and then an infinite summation where the individual terms are ratios. In the numerator, we have the s power of minus z squared. In the denominator, we have the factorial of s times 2s plus 1. Okay, I have focused on the form of these series because this form is important. Now, this series is absolutely convergent for any z, so you could use it in principle for calculating the value of the error function for any complex value of the variable z. However, if you try to do that, you will discover that although in principle this is possible, if you write a code on your computer to do that, you will discover that the use of this series is actually very inconvenient unless your argument z is small in absolute value. And why is that? Well, the first problem is that the series is slow, so it converges, but it converges quite slowly. So, for example, the individual terms of the series do not begin to decrease in absolute value, which is, of course, a necessary condition to achieve convergence, until the index of the series is of the order of the absolute value of z squared. Okay, and their sum does not even begin to approximate roughly the exact value of the error function until about 3 times as many terms have been summed. So you need to sum for a very large value of z, of the absolute value of z, you need to sum a huge number of terms. But unfortunately, that's not the only problem. The most important problem with this series is that if the absolute value of z is very large, then the error function tends to 0, and it does so quite fast. So the value you are trying to calculate is a very small number. However, the individual terms of the series are not small numbers. In particular, the first ones are very large if compared with the sum, the exact sum of the series. Now, this situation, since the series is of course made of terms which are not of the same sign if you calculate it on the real axis, so there will be positive and negative terms which partially cancel each other, because in the end the result is a very small number. This situation is a very dangerous one from a numerical point of view, because if you are trying to calculate a very small number by summing terms which are very large but which partially cancel one each other, then this means that you need to represent those large numbers with a huge number of significant digits. Otherwise, when you perform the cancellation, you lose significant digits and you will never be able to recover the answer you're looking for with a reasonable number of accuracy. Okay. So in the end, if you have a really very large absolute value of z, it's hopeless to use that series on a PC with a finite number of digits. Okay. But fortunately, there is an alternative and very simple approach which allows you to calculate that series for very large values of z. And that's the asymptotic approach. The asymptotic approach has the advantage of producing an alternative series, which in contrast to this one, has an accuracy that increases with the absolute value of the argument. So in this case, it is convenient to have a very large absolute value of the argument. And to see how this works, let us consider to start the phase sector in which the argument of z is not larger than, or better, is strictly smaller than pi over 2 in absolute value. So we are considering the open right half plane of the complex z plane. And let us recall what I reminded you at the beginning. So the Gaussian integral, in which the integration limits are 0 and plus infinity. That's a real integral whose value is the square root of pi divided by 2. So it is possible to write the error function alternatively by including the integration tail that goes from z to infinity, so obtaining 1 since we have normalized the function, and then resubtracting the integration tail that goes from z to infinity. So that's an alternative equivalent representation of the error function. The original definition has an integral that goes from 0 to z, so we now go to 0 to infinity, but we have to subtract what we have added, so the integral from z to infinity. Okay. Why it is convenient to adopt this alternative representation? Well, that's mainly because we observe that the integrand, so the Gaussian exponential e2 minus u squared, is a function that is monotonically decreasing. It attains its maximum when u is equal to 0, and it goes to 0, tends to 0, extremely fast when u increases. Okay. So when you integrate from z to infinity, basically it's a neighborhood of z that gives you most of the contribution to the value of this integral. Okay. And since this is true, we will expand the integrand in a series representation about the lower integration limit, that is about u equals 0. In order to do that, it is convenient to make a change of variable. So we will introduce a new integration variable, w, defined as the difference of the squares, u squared minus z squared, so that the lower integration limit now, that was u equals z, now becomes w equals 0, whereas the upper integration limit remains at plus infinity. Not that we are integrating along the positive real axis of w. The exponential now becomes e2 minus w, so a simple exponential, not a Gaussian exponential. Then there is the Jacobian that produces this additional term, which is 1 over the square root of 1 plus w over z squared. And in addition, we have this factor e2 minus z squared that pops out of the integral, and also the factor 1 over z that also comes out of the integral. Okay. Now, having redefined things in this way, we have an integral along the entire positive real axis of w. And now we make use of the so-called binomial theorem, which provides a representation of the term in brackets, so this inverse square root, as a Taylor series, actually, because it's a power series, which is written as you can see here at the bottom. That's a series with r that goes from 0 to infinity. There is the power of minus w over z squared, which is what we are summing to 1, or better, what we are subtracting to 1 here. And then the coefficients can be written as 1 over the square root of pi, which is taken outside of the summation, and the ratio between r minus 1/2 factorial divided by r factorial. Now, it may be a little puzzling to see a factorial after this number r minus 1 over 2, which is of course not an integer number. So let us make a short detour into the factorial of non-integer numbers. We can generalize the factorial operator to non-integer numbers, and actually to complex numbers, by making use of an important function of complex variable, which is the so-called gamma function. The factorial is defined in particular in this way: z minus 1 factorial, where now z is an arbitrary complex, well, arbitrary. It's a general complex number whose real part is greater than 0, so we are on the right half plane of the complex z-plane. Z minus 1 factorial is defined as the gamma function evaluated at z, and the gamma function is defined in terms of this integral, where again we have a simple exponential e2 minus w, and then there is a power w to z minus 1. Okay. Why is it necessary to enforce the condition that the real part of z is larger than 0? Well, this makes the integral convergent in a neighborhood of the origin. The problem is the term w to z minus 1, because that term could go to infinity violently, so making the integrand not integrable in a neighborhood of the origin, if the real part of z were equal to 0 or less than 0. Okay, so in order to avoid this problem, we will restrict the evaluation of the gamma function with this integral representation to numbers with a positive real part. Now, the gamma function defined in this way can then continued analytically in the entire complex plane with the exception of a discrete set of points that are the non-positive integers, so 0, -1, -2, etc., which turn out to be simple poles. So if you plot the absolute value of the gamma function, you obtain something like I've shown here in this figure, where you can see on the positive real axis, the gamma function is monotonically increasing as the factorial, so it's very rapidly increasing. On the negative real axis, you see those pinnacles, and each of those pinnacles is a pole, okay? Because any complex function having a pole has an absolute value that goes to infinity in a neighborhood of the pole. So you can see these explicitly in this pictorial representation, okay? If you remove the poles, the function is analytic anywhere else. So that's a meromorphic function by definition. So a function whose singularities are poles. And there is an infinite number of poles. Okay, having said that, let us come back to our binomial expansion. If you insert the binomial expansion of this term on the left-hand side inside the integral, and then you again switch the integration and the summation, so you integrate term by term, what you obtain is this. You can now integrate just this term here, e2 minus w times w to the rth power. And by definition, again, through the definition of the gamma function, that's equal to the factorial of r. This cancels the factorial in the denominator here. So what you get in the end is 1 minus e2 minus z squared divided by z pi. And then there is an infinite series. That's a ratio of a factorial in the numerator, r minus 1/2, and the power in the denominator, minus z squared to the rth power. This is valid, again, if the argument of z is in absolute value less than pi over 2. And that's an example of an asymptotic expansion of the error function, valid in the indicated phase range, that is in a certain sector of the complex plane. And let us examine now the behavior of this asymptotic expansion by comparing it with the initial convergent expansion of the same error function. Here you can see this comparison explicitly. The individual terms of the two series are very different. In this case, we have a factorial in the numerator and the power in the denominator, whereas in the convergent expansion, we had the opposite. So the power was in the numerator and the factorial was in the denominator. Okay, recall that the factorial goes to infinity much faster than any power. Okay, now for moderate or large absolute values of z, the asymptotic series has the property that its term first decrease in magnitude, then they reach a minimum, which is around the point the index when the index r is about the absolute value of z squared, and thereafter they increase indefinitely. That's the opposite behavior with respect to the convergent expansion, in which the first terms increase, they reach a maximum around the same index, and thereafter they decrease as they need to do because the series must converge. Okay. So since the asymptotic series has individual terms that do not tend to 0 in absolute value, that cannot be a convergent series. That's a divergent series. However, even if it is divergent, we will never use it trying to sum its terms, but rather we will use just, for example, the first of its terms over the first few terms, because if you stop the asymptotic series at those few terms, what you obtain is a very accurate representation of the error function, especially for very large values of z in absolute value. So basically, the use of an asymptotic series is to truncate it and then use the truncated series as a good representation of the function you are trying to evaluate. Okay, we will now stop to read some inspiring quotes about this fact that the series we are going to use and to study is not a convergent series. Here you can see an amusing one by the mathematician Giancarlo Rota about divergent series. Carlo Rora was addressing some colleagues in a conference of mathematicians, and he said that one remarkable fact of applied mathematics is the ubiquitous appearance of the divergent series. So divergent series are not the exception, they are rather the rule. However, they are hypocritically renamed asymptotic expansions. And he went on saying, isn't it a scandal that we teach convergent series to our sophomores? Sophomores are the students in the first year. Okay, so when you are exposed for the first time to calculus, as we were when we were young, we were taught about convergence. But divergence was seen as a rather pathological behavior. Okay. And do not tell them that few, if any, of the series they meet will converge. The challenge of explaining what an asymptotic expansion is ranks among the outstanding taboo problems of mathematics. That was about 25 years ago. I don't know, it was interesting that at that time a mathematician could write these words. Note that the history of divergent series has been quite complicated. For example, Abel, the mathematician Abel, one of the greatest mathematicians of the first half of 19th century, once wrote that divergent series are the devil, and it is a shame to base on them any demonstration whatsoever. So he was scared of divergent series. In the middle of 19th century, however, something happened so that divergent series were not considered so dangerous 50 years ago, 50 years after Abel, so that Heaviside once say that the series is divergent, therefore we may be able to do something with it. So the attitude towards this kind of behavior had changed. They had discovered that even if divergent, a series could be very useful in practice. Now, actually, asymptotic expansions in the form of divergent series are very useful because basically in any application area of theoretical and also applied science, it is very desirable to have a solution of a problem not necessarily by a numerically exact approach, but by a method, let us call it, of successive approximations, in which the very first term of these successive approximations will provide you at least with an idea of what the answer is. Now, actually, in order to obtain this kind of result, convergent and asymptotic series are not the same. Asymptotic series, even if divergent, are what you need because they are used exactly in this way. They are truncated very often to the very first term, and that term gives you a lot of information about the wave process you are studying. And actually, asymptotic expansions in the form of divergent series appear in virtually any application area. Think examples are the so-called WKB methods, Wenzel, Kramer's, Brillouin methods that are also called phase integral expansions. They are very used in for example, quantum mechanics, but also in the theory of propagation in non-uniform media. Then there is the vast class of the so-called stationary point methods. We will address them next week. And then the perturbative expansions on which, for example, quantum field theory is mostly based, with applications again ranging from oceanography to seismology through optics, applied electromagnetics, quantum mechanics, and so on. So in any case, when you have a wave, typically it is possible to use some asymptotic expansion in the form of a divergent series. Just to give you an example of this fact, imagine that the factorial, so n factorial, can be approximated and is approximated extremely often by means of the so-called Stirling Laplace asymptotic formula. Maybe you have found it sometimes. It's very common, for example, in statistical mechanics, in which the factorial is approximated up to a multiplicative constant as an exponential times the power of a power. So n2 n plus 1/2. Okay. However, the factorial would have in principle also a representation in terms of a convergent expansion whose first two terms are here listed, 1 minus 0.5772 times n plus all the other terms proportional to n squared and cube and so on. However, this latter convergent expansion is virtually non-existent in the scientific literature, whereas the Stirling asymptotic formula, which is actually the first term of a divergent representation, that's the okay. Just to finish with this introductory survey, as we noted, the asymptotic and convergent type of the individual terms of the series are very different. The asymptotic one has a factorial in the numerator and a power in the denominator. The exponential type has the factorial in the denominator. That makes the difference. There is also an intermediate possibility in which you have a factorial both in the numerator and in the denominator. And that's a kind of series that is probably the most complicated one. This kind of series are those that define the so-called hypergeometric functions, which is a vast class of special functions. So we will call this intermediate kind of series as the hypergeometric type, whereas the series on the left is certainly divergent, whereas the one on the right is convergent in the entire complex plane. The intermediate possibility gives you a conditionally convergent series. So what you get is a finite radius of convergence. And that typically appears in the treatment of cooperative phenomena, so where many small things interact together. For example, in thermodynamics, when you have systems made of a huge number of particles, in a neighborhood of a phase transition, this may happen, so the hypergeometric function pops out. Examples are the Ising model in statistical mechanics. Also ferromagnetism, in which you have the domains, okay, in which interact one with its neighborhood. Also in the solid state physics, we have this kind of series, for example, in the theory of Fermi-Thomas electron screening, but also in macroscopic, not quantum physics like hydrodynamics. For example, if you consider the behavior of a fluid close to solid surfaces, you have the theory of the boundary layers, in which there is a small layer of fluid in which the things go very differently than in the bulk of the fluid flowing outside. So this kind of transitions are typically associated with a finite radius of convergence. We will not deal with this intermediate type. However, this was just to mention that that's another interesting possibility that may occur in practice. Okay. Now, it's interesting that what we did so far for the error function was based on the assumption that we worked on the right of the imaginary axis. However, one could be interested in evaluating the error function outside this half plane. So let us consider what happens, for example, right on the imaginary axis. So when z is equal to a purely imaginary number, like j times y, where y now is a real number. By again changing variables, so letting u equal to jv, we can rewrite our error function evaluated on the imaginary axis as in this way, where now the integration variable is v and the exponential is e to v squared. So there is not the minus sign in the exponent anymore. Note that we also have this j that has appeared outside the integral. Now, the integrand in this case is large, only close to the upper integration limit, not the lower. That's because the exponential is now monotonically increasing. And therefore, it is convenient to expand the integrand about the upper integration limit. So again, we will change variable. We introduce a new variable, f, defined as the difference between y squared and v squared. And we proceed exactly as before. So what we obtain is an integral that goes from 0 to y squared. Then there is this exponential, and now from the Jacobian of the change of variables, we obtain this term here. So it's again the reciprocal of a square root of 1 minus f divided by y squared. Now, since the integrand is real throughout the integration limit that goes from 0 to y squared, however, if you try to evaluate the integrand outside this range, so for values of f greater than y squared, you can see that the term in brackets would become negative, and therefore its square root would become purely imaginary. Okay, so it is possible to extend the integration limits to plus infinity. However, you just need to take the real part. So you eliminate the contribution that goes from y squared to plus infinity. But it's convenient to do that because now we will proceed as before. We will expand this inverse square root with the binomial theorem, and we will integrate term by term. Okay. If we do that, that's the second row in this development, then you can integrate this function elementarily. So you get again the factorial of r that cancels the same term in the denominator. You end up with a series that is made of real terms, so you don't need to explicitly take the real part. So in the last result, you can see there is not the real part because it's useless. Okay, so again, we have arrived at an asymptotic series. And you can do the same kind of reasoning when z is negative imaginary. So in both cases, the result is the one that is represented in the box below. This is the asymptotic expansion of the error function when you are on the imaginary axis. Now, the interesting thing is that what we have arrived at is not the same as before. That is, when we worked on the right of the imaginary axis, what we obtained was a different type of expansion. You can compare them. The first one we obtain is the upper here. The second one is almost the same, but without this constant one in front of the series. So there is a discontinuity in the asymptotic representation. This is known as a Stokes discontinuity, and since it occurs along a ray, that is the positive imaginary or the negative imaginary axis, those are called Stokes rays. So they are specific values of the argument of z, where the asymptotic expansion has a discontinuity. Note that the asymptotic expansion is discontinuous, but what we are trying to represent, that is the error function, is not. That is, it is a continuous function. That's even an analytic function of a complex variable. However, even if the function is analytic, its asymptotic representations need not be analytic, and in fact, they have discontinuities. If we go on the left of the imaginary axis, we obtain a third possible representation. In order to do that, the most convenient thing is to reverse the sign of u, which is the original integration variable, in the defining formula. If you do that, you obtain a relation between the error function evaluated at z and the error function evaluated at minus z. So you have a continuation formula. That is, you can continue the error function from the right half plane to the left half plane. If you do that and you apply this to the initial asymptotics we obtained, you have this result in the box. So where now note that the constant, which is known as an associated function, has changed because now it is equal to -1, whereas originally it was equal to +1. So the Stokes rays, the positive and negative imaginary axis, determined a change in this constant, okay, from +1 on the right of the axis to -1 on the left, okay? And that's typical in many instances, as we will see also later. Okay, having concluded this behavioral survey that was centered on the error function, I think we are ready to make a 15 minutes break. And so see you after the break to go on with some general information about asymptotic series that go beyond this very specific example considered so far. Okay, see you later.
See you later.
Okay, here I am back. Okay, let us examine now some definitions and fundamental concepts related to asymptotic expansions. We will start with an example again. We have now a function of a parameter epsilon, which is real and positive. And it is again defined in terms of an integral. That's the integral from 0 to infinity of the ratio between a simple exponential e2 minus t that guarantees convergence at infinity of the integral. And in the denominator, we have 1 plus epsilon t. So that's an integrand without singularities in the integration range. So no problem. When epsilon tends to 0, we wish to evaluate this asymptotically. So in the limit of small epsilon. One thing you can do, and that's one of the simplest example of an asymptotic approach, is to integrate by parts. If you do that, you obtain 1 definite contribution of the integration by parts minus epsilon that pops out from the antiderivative of the term that multiplies the exponential. Then there is the integral of the exponential divided by the second power of the previous denominator. And it is possible to iterate, so you can integrate by parts this latter integral. What you obtain is a term that goes like 2 times epsilon squared plus some other terms that go like epsilon cube up to epsilon to the nth power. And the remainder, so what remains after those monomials, is an expression that has some numerical constants. Then there is the power epsilon to n plus 1, and then an integral in which you can see there is the power n plus 2, where n is capital N, okay, the number of iterations you have done, minus 1. What kind of series is this? Well, that's an asymptotic series, and now we will give the precise definition. That's again the result we will say that take the first term after the constant 1, that is minus epsilon in this development. We will say that this is a term of order epsilon, whereas the next term that goes like epsilon squared, so it's 2 factorial, which is equal to 2 times epsilon squared. This term is of smaller order than epsilon. We will be more precise in a moment, but intuitively, if epsilon is a small number, then epsilon squared will be even smaller. Okay. If you truncate this development up to these first 3 terms, so 1 minus epsilon plus twice epsilon squared, what you obtain is an approximation of the left-hand side that is said to be correct to order epsilon squared. That's because that's the highest order you have retained before truncating. Okay, of course, this assumes that epsilon is a small quantity, and to be more precise, we will say that the function f of k is of order of the function g of k, and we will write this in the so-called Landau notation by using this big O. So we will say that f of k is a big O of g of k, when in the limit when k tends to some number k0, then there are constants m positive and delta positive, such that the absolute value of the function f is bounded above by the absolute value of the function g times the constant m, and this is true for any value of k in a neighborhood of the point k0, the neighborhood going from k0 minus delta to k0 plus delta. Okay. On the other hand, we will say that the function f is instead much smaller than the function g in the same limit, and we will also write this with a double sign of inequality, like there. If the ratio of the two functions, in which f is in the numerator and g is in the denominator, that ratio tends to 0 in the limit when k tends to k0. So intuitively, the function f is more rapid in going to 0 than the function g. Okay. Finally, we will say that f of k is an approximation to I of k valid to order delta of k, again in the limit when k tends to k0, when the limit of the ratio between the difference of the function I and the function f, which are respectively the function you are wishing to approximate and the approximating function, well, the ratio between that difference and delta of k tends to 0. So the difference is faster in going to 0 than delta. Then in that case, we say that this approximation is valid to order delta. Okay. Now, it turns out that the sequence of monomials 1, epsilon, epsilon squared, epsilon cubed is characterized by the fact that any term is much smaller than the previous one. Here there is a typo. The j plus 1 term is much smaller than the j term. Okay, so you have to switch those. And by definition, if this occurs, then the sequence is said to be an asymptotic sequence. Okay, so epsilon is much more smaller than 1, but epsilon squared is much smaller than epsilon, and so on. And the representation of the integral we started with consists of a truncated asymptotic sequence plus a remainder, the very last term. We would say that this provides an asymptotic expansion with respect to this asymptotic sequence. By adopting this definition, therefore, if you have an ordered sequence of functions, delta of sub j of k, where j is an index that goes from 1 to infinity, then we say that this is an asymptotic sequence if the j plus 1 term is much smaller than the j term, as we said before, in the limit when k tends to k0. Now, if I is a continuous function of k, and we have an asymptotic sequence delta j of k in the limit when k tends to 0, then we say that span of a coefficient a sub j times delta j of k provides you with an asymptotic expansion of I of k, which is valid to order delta capital N of k if it turns out that if you truncate that summation up to the index m, lowercase m, then the remainder, that is the error you are incurring it, is of the order of the first neglected term in the asymptotic sequence. So if you truncate up to the order m, what you are doing, what you are obtaining is an approximation valid to order delta m plus 1. Okay. It is also possible that the upper index capital N, sorry, I think I lost the connection. Okay. It is also possible that the upper limit n is equal to infinity. So what you get is an infinite asymptotic series. We write all these things synthetically by using the tilde symbol. So if we write that the left-hand side, the function I of k, is represented asymptotically by the right-hand side, we use the symbol tilde, which means exactly what we have said so far. So if you truncate this expansion up to a certain index, then the error is of the order of the next term in the asymptotic sequence. Note that the tilde is also used in a slightly different way to compare two functions. That is, we use the tilde to compare two functions I and eta, meaning that their ratio in absolute value tends to 1. Okay. However, in this case, when on the right-hand side we have an asymptotic representation, or better, an asymptotic series with respect to some asymptotic sequence, the precise meaning is exactly the one I gave you, so that it is possible to evaluate any of those coefficients, a sub j, simply by subtracting from the left-hand side, so from I of k, the truncated version of the right-hand side up to the index n minus 1, and then divide this difference by delta sub n. Because if you do that, by definition, you obtain the coefficient a sub n. All the other coefficients going to 0 in the difference. If you can do that with an arbitrary number of terms, what you get is properly an asymptotic series representation of the left-hand side. Okay, so again, if you truncate an asymptotic series representation up to a certain index, what you obtain is a representation in which the error is of the order of the first neglected term. Okay, so if you truncate up to order 1, you obtain an error which of the order 2, and so on. Now note that having an asymptotic series does not imply in any way that the series is convergent. And the example we are examining is very clear. In the example we are considering, the asymptotic series is a series of monomials whose coefficients are of this kind, -1 to the jth power times j factorial, where j goes from 0 to infinity. This was obtained integrating by parts iteratively. Okay. Now this series is manifestly not convergent. That's because if you consider any value of epsilon, then the factorial makes the individual terms divergent at infinity in absolute value when j goes to infinity. So in no way this series is a convergent series. However, if instead of fixing epsilon, you fix j, so you consider a finite number of terms in this series, and you consider the limit in which epsilon goes to 0, then this may provide you with a good an accurate representation of the function on the left-hand side. And this is actually the way we use this kind of asymptotic series. That is, we use them in the limit when, in this case, the parameter epsilon goes to 0. Another example related in an asymptotic expansion of the function j of k, where now k goes to infinity. The integrand of the integral that goes again from 0 to infinity is similar to the previous one. Now the parameter, however, is in the exponent of the exponential. However, by a simple change of variables, we can reduce ourselves to the previous case, because by letting t prime equal to k times t, and epsilon be equal to 1 divided by k, so the reciprocal of k, what we see is that in the limit when k goes to infinity, the new parameter epsilon goes to 0. The integration limits remain the same, and now the exponential becomes e2 minus t prime in the numerator. In the denominator, we obtain 1 plus epsilon t prime, and there is also an epsilon factor that pops out of the integral because of the Jacobian. Now, what we have obtained is the previous integral, for which we have an asymptotic expansion in terms of epsilon, or equivalently in terms of powers of 1 over k. So our j function of k is given by this asymptotic development, 1 over k minus 1 over k squared plus 2 divided by k cube, and so on, plus a remainder. Let's call the remainder r, that stands for remainder of order n, which is given in terms of this integral here. And it's easy to evaluate this integral, or better, to estimate above this integral. Because if you observe the definition of the remainder and you calculate its absolute value, you will discover that this absolute value is less than or equal than the ratio in front of the integral, so n factorial divided by k to n plus 1. And the integral itself can be estimated above by simply replacing the denominator with 1. So you obtain the integral of the exponential, which is equal to 1. Now, this upper limit for the absolute value of the remainder is much smaller than 1 over kn, which is the last of the terms in the expansion we are considering. So we comply with the definition of an asymptotic expansion. So if we truncate to order n, what remains is of order n plus 1, which is the next term in the asymptotic sequence. So we can legitimately use the tilde symbol and express our function j of k in the asymptotic form of a series of inverse powers of k, okay, which is again a divergent series. A third example, the asymptotic expansion of the function I of k, where now k is the lower integration limit, and the integrand is just e to minus t divided by t. Note that now this denominator would cause a problem in the origin if we try to integrate in the neighborhood of the origin. However, now the lower integration limit is k, and k goes to infinity, so we don't need to deal with the origin at all. So within the integration range, the function is regular and integrable at infinity because of the exponential. Okay. Now again, we can integrate by parts. If you do that, we will discover that all the terms you obtain contain the exponential factor e to minus k. So it can be factored out in front of the square brackets, which contain again the asymptotic sequence 1 over k, 1 over k squared, and so on. And again, we have a remainder. But as in the previous example, this remainder can be estimated. We can obtain an upper limit for the remainder with the same approach as before. So we can estimate the value of this integral, e to minus t divided by t to the n plus 1 power, by replacing the denominator with its smallest value, which is k. So this pops out of the integral. And what remains can be evaluated now explicitly because we have the integral of the exponential function that gives you e to minus k. I guess that this lower integration limit that is 0 here is a typo. That should be a k. Okay. So again, we can observe that this upper limit for the absolute value of the remainder is much smaller than the last term of the finite summation in square brackets, which is multiplied by the exponential. That's because in the denominator we have k to n plus 1, whereas the last term in brackets has a k to the nth power in the denominator. So again, we are in the condition of stating that this is an asymptotic representation. And if you let n go to infinity, what you get is an infinite asymptotic series representation. That, in this case, has the exponential e to minus k in front of all its terms. Okay. So we have examined what is probably the simplest asymptotic technique, that is integration by parts. Unfortunately, this does not work always. So in the next week, we will deal with much more sophisticated approaches. However, sometimes it works. Now, some words about the accuracy of the asymptotic expansions. Asymptotic series, as I said, are not to be summed because they are not convergent. They are used typically by retaining one or a few terms. For example, if you consider the last example, and you take the argument k be equal to 10, which is large but not so large as a number. Typically, that's the threshold for defining large numbers. Okay, so we say that something is large if it is larger than 10, which is quite arbitrary, but it's very common. And if you retain the first two terms in the series, the asymptotic series, then since you can evaluate exactly this function, you can compare the exact result with the first two terms of the series, and in particular with the remainder, which is the error you are committing. Then you will discover that the error is of the order of 10 to minus 13, which is, of course, in absolute value very small, but you should compare it with the exact answer. The exact answer is of the order of 10 to minus 6. So it's very small also in relative terms. So there are 7 orders of magnitude less than the exact answer. So by using just 2 terms in the asymptotic expansion, you are getting an answer which is accurate to 7 digits of precision, which is something huge if you try to obtain that with alternative approaches, say numerical approaches, for instance. 7 digits is something that typically cannot be achieved by using standard numerical methods unless you are very lucky, okay? But even if the argument is not so large, so let's choose k equal to 3, which is not a large number, and again we use 2 terms in the series, the remainder is of the order 10 to minus 3, and now you can compare it with the exact result, which is of the order of 10 to minus 2. So if you wish to have just a rough estimate, accurate to 10%, because here you are comparing 10 to minus 3 to 10 to minus 2, so you are making an error of the order of 10%, then your asymptotic series is still good. And for many purposes, having a 10% accuracy is enough. So if you just want to observe the trend of some phenomenon, okay? So of course, it depends on the application. If you wish to have a satellite be in orbit around the Earth, then you need many digits of accuracy. If you just want to observe the trend of some phenomenon, you need many fewer digits of accuracy. Now, for any asymptotic series, it is possible in principle to find the optimal value of n, that is the optimal way of truncating the series. That's because, as I said before, the individual terms of the series typically decrease in absolute value. There is a minimum, and then they start increasing. So if you truncate around this minimum, what you obtain is the highest accuracy. That's called sometimes informally superasymptotics. But the ordinary asymptotics consists in just using the first term of the asymptotic series, which is, or the first 2 terms, which are typically enough to obtain a good accuracy. Now we will state some general properties of asymptotic expansions. If you are given an asymptotic sequence delta j of k, then the asymptotic expansion of a function f of k with respect to that asymptotic sequence is unique. So we have a uniqueness theorem. And that's very simple to prove the uniqueness, because if you, by contradiction, if you assume that you have 2 different asymptotic expansions, one with coefficients a sub j, and the other one with coefficients b sub j, then you can subtract term by term, so obtaining on the left-hand side 0, and on the right-hand side another asymptotic expansion in which the coefficients are now called c sub j, are simply the differences between the a's and the b's. However, if you divide it now, for example, by delta 1, the right-hand side, and you take the asymptotic limit, you obtain that the first coefficient, c1, which is the only one that survives in this asymptotic limit, must be equal to 0, which is the left-hand side. And if this is true, then you can divide everything by delta 2, discovering that also c2 is equal to 0, and so on. So you discover that all those coefficients, cj, are equal to 0, which means that the a's and the b's were actually the same. So we have uniqueness. Okay. Now, in the examples we have considered so far, we have considered real values of the parameters, epsilon that was small, k that was large. However, it is possible to extend those considerations to complex values of the parameter. So we will now call the parameter z to remind us that that's a complex number. If we have a function, for example, f of z, that is analytic everywhere outside the circle of radius r, and center in the origin of the complex plane, so the circle where the absolute value of z is equal to r, then we know that this function will have a convergent Taylor series at infinity. That's because we are assuming that it's analytic everywhere, included the point at infinity. So that's an analytic function on the Riemann sphere. So we can represent our function as a Taylor series in inverse powers of z. And in this case, we have an example of a convergent Taylor series by assumption, since this is analytic, which is, however, also a convergent asymptotic series. So the Taylor series provides you with also an asymptotic representation. In this case, with respect to the asymptotic sequence of the inverses of powers 1 over z to the jth power. However, this is possible only if f is analytic at infinity. If f is not analytic at infinity, however, it can be shown that it cannot possess an asymptotic expansion valid for all values of the argument. So typically, the asymptotic expansions of functions that are not analytic at infinity are valid only within some angular sector of the complex plane, as in the example of the error function we introduced in the first part of this lesson. That is, the expansion is constrained by some bounds on the argument of z. That's the occurrence of the Stokes lines of discontinuity. A function f is said to have an asymptotic power series then in a sector of the z-plane in the limit when z goes to infinity, if we can write this, that the function f is asymptotic, hence the tilde sign, to this series of inverse powers of z, which again means that if then the error is of the order of the first neglected term. And the series in general will not be convergent. Now, if you have another function g, and you have therefore another asymptotic power series representation with coefficients b instead of a, then it is true that if you perform the arithmetic combination f plus g, that is, if you sum the two functions, or the product f times g, then also those combinations have asymptotic power series representations, then they can be obtained by adding or multiplying the two series valid for the individual functions f and g. Okay. Even more, if you have an asymptotic power series, then you can differentiate or integrate it term by term in order to obtain an asymptotic expansion of the first derivative of f, or of the antiderivative, the primitive of f. For example, in this case, you have the asymptotic expansion of f prime, whereas here you can see the asymptotic expansion of the difference between f of zeta and a0 plus a1 divided by z. This is true because we are dealing with the asymptotic power series. That is because the asymptotic sequence we are considering is made of monomials. In general, if you consider a different asymptotic sequence, it would not be true that you can differentiate term by term. However, it remains true that you can integrate term by term. That is typical because integration is an operation that tends to give you smoother results, whereas differentiation tends to decrease the level of smoothness. So if you have a general asymptotic sequence, it is not possible to differentiate in general terms by term. Excuse me. Now, an interesting thing is the possible existence of terms beyond all orders, as they say. They come about in explaining why a given asymptotic expansion can represent two entirely different functions. We observed that there is a uniqueness property. So if you are given the function, then a given function has a unique asymptotic expansion. But the reverse is not true. If you have an asymptotic expansion, or better, if you have an asymptotic series, that can be the asymptotic expansion of two entirely different functions. So it's not unique, the function. Suppose, for example, that we consider z that goes to infinity in the right half plane of the complex z-plane, and that the function f is asymptotically represented in that sector by a certain asymptotic series of inverse powers of z with coefficients a sub j. Now examine the function that you obtain by adding to f the exponential e2 minus z. Now this exponential function in this sector has by itself an asymptotic expansion in inverse powers of z with coefficients bj. However, all those bj coefficients are equal to 0. That's because the exponential goes to 0 faster than any power. So if you try to calculate all those coefficients by evaluating the limit of the product of the generic monomial z to n times e2 minus z, that limit is equal to 0 for any n, because any power goes to infinity less fast than the exponential. Okay. This means that the sum of the function f plus the exponential has an asymptotic series, which, as we said, is the sum of the two asymptotic series. However, bj's are equal to 0, so the asymptotic series is exactly the same as the one valid for e2 minus z is transcendentally small, or is beyond all orders, okay, with respect to this asymptotic power series. This means that it seems that an asymptotic power series will give you no information about these terms. So we will never be able to recover an exponential like that from an asymptotic series. Well, that can be considered as a kind of drawback in the definition of an asymptotic expansion. And this definition we have given is the classical one given by Henri Poincaré at the end of 19th century. And this was actually the basis of the development of the theory of divergent series. However, keep in mind that there are also different definitions. For example, the physicist Robert Dingle in the 50s and 60s of the last century proposed a different approach, where he proposed what he calls a complete asymptotic expansion. And he was able to show that actually there is a latently exact meaning. So it's a hidden meaning in an asymptotic series, in what he calls a complete asymptotic series, that allows you for recovering the function you started with. Okay, this is explained in his book, which is quite difficult to read, but it's very interesting. These asymptotic expansions, their derivation and interpretation, from which I've taken the introductory behavioral survey based on the error function. However, keep in mind that those exponentially small terms may sometimes be very important in physical terms. For example, typically non-perturbative effects, that is, effects that cannot be obtained by a perturbative expansion, that is, an asymptotic expansion in terms of small parameter, may be important in physics. One classical example is that of superconductivity, whose theory was derived after many efforts of many brilliant physicists, which were not able to derive a correct theory because they insisted in performing perturbative expansions, whereas the phenomenon is intrinsically non-perturbative. So an entirely different route was to be taken, and it was taken by those who found the Bcs theory of superconductivity. If you are interested in this, I can advise you to read this beautiful review article by John Boyd, who, by the way, is a civil engineer, whose name is interesting, The Devil's Invention. This refers to Abel's idea that divergent series are something due to devil, asymptotic, superasymptotic, and hyperasymptotic series. And there is also this review article more focused on theoretical physics, which gives you an introduction to a mathematical theory related to all of these, which is the so-called resurgence theory, from which you can resurrect exponentially small terms which seem to be lost in the asymptotic development. Okay, let us finish by again mentioning the issue of discontinuities in complex asymptotic expansions. If you have a function f of z, which has an asymptotic representation in a given sector of the complex plane, it may happen, as we saw, that the same function has an entirely different representation in a different sector of the complex plane. In fact, even if the function is analytic for any z, so it's an entire function, so for any finite value of z, it is possible that its asymptotic representation changes discontinuously by crossing one sector to go into another one. And you can have elementary examples of this. If you take the hyperbolic sign of the inverse of z, and if you perform the limit when z tends to the origin of the complex plane, you will discover that if you approach the origin from the cyan area, that is from the right half plane, then this function is asymptotic to 1/2 of the exponential of 1 over z. Whereas if you are in the yellow part, on the left half plane, you are asymptotic to 1/2 of e to minus 1 over z. So there is a minus in the numerator. Okay. So it depends on the sector you are considering what kind of asymptotic behavior you get. Here is an overview of the possibility if the simplest case is that of a function analytic at infinity, for which therefore you have a Taylor series representation of the function in terms of inverse powers of z, and in that case the Taylor series provides you with an asymptotic series which is convergent, because sometimes asymptotic series converge. An example could be for 1 over z plus 1. However, this function should be considered outside the unit disk, so when the absolute value of z is larger than 1. In this case, it's easy to see that there is this kind of Taylor representation in inverse powers of z, which is also an asymptotic representation by the properties of Taylor series. In this case, the representation holds for any value of the argument, so everywhere in an entire neighborhood of infinity. However, if your function has a branch point, like a square root has, then in that case you need to cut the plane along some branch cut. For example, in the case of the square root, you have a branch point at the origin that needs to be connected to infinity if you wish to fix a given continuous branch, single valued branch of the square root. In that case, since the branch cut goes all the way to infinity, you cannot expect that the asymptotics is continuous across the branch cut. So you have a discontinuity due to the existence of a branch cut. And finally, we have the possibility that the point at infinity is an essential singularity. And in this case, which is, for example, the case of the exponential function, the error functions, and many others, even though the function is single valued in the neighborhood of infinity, so there is no branch cut, and the asymptotic expansion still has some lines across which it is discontinuous. They are called rays, Stokes rays, and the phenomenon was discovered by the physicist and mathematician George Stokes in the 19th century, and for this reason they are known as Stokes discontinuities, Stokes rays, and the phenomenon is the Stokes phenomenon. The example that we gave before about the hyperbolic sign gives you Stokes lines along the positive imaginary axis and also along the negative imaginary axis. Okay. Just to give you an idea of the possibilities. Okay, I will stop here today. Some references that may be useful to go in depth about this are the book by Ablowitz and Focas about complex variables, which contains also an introduction to asymptotics. This is a nice book about complex variables of a very applied character, so it's much less theoretical than the references I gave you last week. And for this reason, I preferred the previous books. However, that's useful because it goes much more directly to the point. So it's like a cookbook. If you want to know how to do something, you can read it fast here. If you want to understand really what's happening, go back to theoretical books. And then there is also this book by Dingle, which, as I said, is a rather advanced one, but it's nice to read because it has a different approach with respect to all the other literature of the subject. Okay, that's all for today. So see you on Thursday when we will see something about ray optics. You will find the recording and the PDF of these slides in a few hours, I hope, on the e-learning website of this course. Thank you very much for your attention and see you next time.
Bye-bye.
Thank you, Professor.
Thank you.
Bye.
Bye bye.
Bye all.
Bye-bye.
Ciao Paolo,
Ciao Fabrizio, buona giornata.
anche a te.